My goodness, people just getting kicked out left and right. Okay, so we're being recorded, but it's not recording you, it's recording my shared screen. You can see my periodic table, yes?
Awesome. Yeah.
Okay, perfect. Okay, so we started the year with, actually, I don't know where exactly it started, but I'm going to go through in my brain how this makes sense to me. So we have elements. Those are all of these different symbols in the periodic table. So H is an element, Cu or copper is an element, T, oh, that's an L, I thought that was an I. Tl, thallium, those are elements. Elements can come together to make compounds. So for instance, NaCl, that's a compound because it has at least 2 elements in it. However, if I write this, that's a pure element. That's just fluorine. Compounds get separated into 2 types, ionic and molecular. So this would be an ionic compound. Ionic compounds have something from this side plus something from this side. That's an ionic compound. Molecules have things only from this side over here and or hydrogen. So actually, when I circled all of this, I should have stopped just below the hydrogen. So ionic, this would be ionic because you have a metal plus a non-metal. That's ionic. If you have only nonmetals, that is molecular, which is the same thing as saying covalent. Right? Molecular and covalent are the same thing. So we've got ionic compounds, molecular compounds, we have elements, we have compounds, we have mixtures. So everything I've talked about so far is just pure things. Then we have these mixtures. Mixtures are when you have at least 2 different things put together, 2 different chemicals, 2 different substances. So mixtures would be like water with salt water would be a mixture. And then mixtures, we can divide those into 2 types. We have homogeneous, everything looks the same. I see only one phase. I see one thing and that's it. Heterogeneous mixtures, I see 2 separate areas. I could see more than 2. I could see 1,000 different separate areas. So this pen, for instance, you know, you see a white part and a black part. This is a homogeneous mixture, this little writing utensil for writing. Okay, now let's erase all this. So then we get into atomic masses and protons and neutrons and electrons. So each element has protons, neutrons, and electrons. The protons are all of these numbers in the upper corner. Okay, those are all the number of protons for each element. Then we have masses, and actually, right here, they give you a key that number is the atomic number. So, you know, if you ever forget protons, look at your key there. That's the atomic number for this periodic table. In our notes, I wrote things this way, where the atomic number is down at the bottom and the mass number is up at the top. That's protons and neutrons. And then we have our net charge over here, where net charge is protons minus electrons. So in those, my pen is not lining up. This should say, there we go, protons minus electrons. So your periodic table, you get your protons from the top left, even though for our isotope symbols, we put the protons in the bottom left. That's a little confusing. These non-whole numbers, we don't use those for anything in the isotopes. You have to be given the number of neutrons to get the mass number. You have to be given either the net charge or the number of electrons to solve for the other one. So the net charge and the electrons are linked. The mass number, if you're given this number up here, then you're going to be asked to solve for the neutrons. If you're given the neutrons, you'll be asked to solve for the mass number. All right, next topic. How do we get these numbers here? So these numbers, all these strange non-whole numbers, those are called the atomic mass or the molar mass. Atomic mass or the molar mass. Atomic mass has what's called the unit AMU. Molar mass has the units grams. This is AMU per molecule. Hold on. Per molecule. Oops. Per molecule. Oops. I can spell. I just can't use this thing right now. Oh my gosh. Per molecule. Come on. Come on. Per molecule. Molar mass would be grams per mole. And the way we get these are those weighted average things where you do the percent of the isotope times the mass plus the percent times the mass. If you have more than 2 isotopes, you keep adding those. And when you add all those numbers together, that's where these numbers come from. So the numbers, those masses that you see on the periodic table, those are the average weighted mass of all the isotopes for each element on Earth. If we went and did this on some other planet, we would actually probably find slightly different atomic masses. So we could have a periodic table for Mars. We could have a periodic table for the Sun. We could have a periodic table on Pluto, and they all might be a little bit different. Okay. So that's where these atomic masses come from. And those are the problems. I think they were page 4 or 5. I'm not sure. But where you do mass times percent plus mass times percent plus mass times percent. So then someone asked me the other day, so these moles, like, why do we use moles? I don't understand. We use moles. That's okay. We use moles because when we have a scale, trying a little scale here. So here's my place where I put my sample on, and then you get a little output. So we see our mass show up here, right? And we put our sample on the scale. So scales measure grams and pounds. They don't measure molecules. We have no way of having a scale, putting a sample on a scale and having that scale tell us how many molecules are sitting on that scale, right? That's impossible. We have very special machines that can do that. And those machines, we send a sample, we send pure samples through a machine, and that machine will tell us how many particles are in there and what the mass is for those particles. That machine is what we use to get these isotopic weighted averages for the masses that we put on the periodic table. Again, these scales, all we can use is grams, right? So we cannot measure moles with a scale. However, when we have chemical reactions, I'm just going to write a random, I'll do water makes oxygen and hydrogen. Okay, so there's a chemical reaction. And actually, I don't want to have I don't want to have fractional coefficients. I'm going to have full numbers. I'm going to change this slightly. And we'll make it 2 waters makes 1 oxygen and 2 hydrogen. So our chemical reactions, those are not based on grams. Those are based on molecules. The scales only measure grams. The reactions, those coefficients in the reactions, these represent moles or molecules. So then comes the question, well, how do we get from these grams to the moles? And that's where we use molar masses. Okay, so are we getting the idea that we need to use these numbers down here to always go from grams that we measure, because that's all we can do is measure grams, to get to moles, because these chemical reactions are all moles. It's almost as if, think about the car example, we can count tires, right? That's really easy. They're big. you would never go to a tire factory and say, okay, I've got 500 grams of tires and I've got 50 grams of steering wheels. How many cars can I make? That would make no sense, because we are capable of counting our tires and our steering wheels. But imagine a world where you couldn't, and we had to actually say you've got 500 grams of tires and this many grams of steering wheels, and now you got to calculate your cars. You would have to convert your masses to the number of tires and the number of steering wheels. So that's what we're doing when we're going from grams to moles. We're converting to a quantity that's used for the reaction that we are testing. And again, you don't have to pay complete attention to this, right? You are totally allowed to do the problems that you want to do. So the next question comes, where does this Avogadro's number come from? So now, let's look. So hydrogen has pretty much, it's 1, 1. Most hydrogen atoms look like this. That's the isotope for most hydrogens. Some hydrogens look like this, and some look like this. This is called deuterium, and this is called tritium. But almost all the hydrogen atoms are this. That's why this molar mass is so close to 1. Protons and neutrons each have a mass of approximately what's called 1 atomic mass unit. Atomic mass unit is a mass. It's the mass of a proton, or the mass of a neutron, approximately. So there are 6.022 times 10 to the 23rd atomic mass units in 1 gram. So when we go from grams to moles and then moles to molecules, this number comes up because we're going from the moles to the actual number of molecules. And these numbers on the periodic table, those are how many atomic mass units are in 1 particle. It's also how many grams are in 1 mole. And the way that this number is figured out, it's all based on carbon-12. Okay. 1 atomic mass unit is equal to the mass of 1 carbon-12 atom. That's how we have defined the atomic mass unit. It's the mass of 1 carbon-12 atom. And the way we measure this is people have purified carbon-12, and then they measure out 12 grams of the carbon-12, exactly 12 grams. So they isolate the isotope that's carbon-12, they put it on a scale and measure exactly 12 grams, and then they take that and they put it through a machine that counts particles. And when that machine counts the particles, the machine gets this many particles in there. So this Avogadro's number is based on carbon-12. Okay. And the definition, I wrote 1 AMU. That's not 1 AMUs, that's 12 AMUs. So 1 AMU is the mass of 1 carbon-12 atom divided by 12. And that's 1 AMU, atomic mass unit. You don't have to know all this. I'm just trying to give you some background of how all these numbers on the periodic table relate to this Avogadro's number, relate to the concept of a mole, and why we convert from grams to moles. Why are the moles so important? And they're important because in chemical reactions, things react in whole number ratios for all of these elements. But all of these elements have different masses because they have different numbers of neutrons and protons. So we have to find a way to equalize them, to make it something that we can work with. And the mole is what we can work with. I'm hoping that's helping. Empirical formulas. Have you ever seen a chemical formula? That's written like this. 0.56, H 1.12, O 0.56. This should be, yeah, I did that right. Okay. Have you ever seen a chemical formula with decimal numbers? Never. So let's make this empirical formula make sense. Chemical formulas always have whole numbers. So when you're given the percent of a chemical in a compound, you're given the grams. Get them to moles. Because these numbers down here, those are all the moles per mole of molecules, or the number of atoms per molecule. So we've got to get to moles. We can never use grams. And then, you know, the second step in the empirical formula is divide by the smallest number. You're doing that to get rid of these decimal numbers here. So you get all your moles and you can put them like they're little subscripts. And then you say to yourself, well, I can't have decimal numbers there. I've got to have whole numbers. So if we divide these all by the smallest one, that will help us convert these. I'm dividing them all by the same. So I'm dividing them. I'm still keeping the ratio of the quantities exactly the same. So this comes out to C1H2O1. Okay, there's my empirical formula. Woohoo! All right. So hopefully empirical formulas are going to make a little more sense now in the big scheme, the big picture. Then we get to molecular formulas. Well, let's just say I gave you an empirical formula and I tell you the mass of the whole molecule. Well, all we need to know is how many of these do we need to get to the complete mass that we're supposed to have. So I would look at this problem and say, CH2O has a mass of 12 plus 2 plus 16. So that's 30 grams per mole. Well, if I tell you that the whole thing has a mass of 180 grams, the molar mass is 180 grams, and I gave you this formula. And I said, what's the molecular formula? Well, remember, all of these things are about ratios, right? So I look at this and I say, well, if this one weighs 30 and my whole thing weighs 180, how many of these do I need to get to that 180? 30 times what is 180? 30 times 6 is 180. So that tells me, oh, I need 6 of these. If one of these weighs 30, and I need to weigh 180, oh, I need 6 of these to get to the 180 grams. Now, we don't put a 6 in front. We don't do that because that's like a chemical reaction. That would say that I have 6 of these. Putting a 6 in front, CH2O. Oh my gosh, I have to write too many of them. CH2O, CH2O. Writing it this way looks like this, where I've got 6 of these things. That is not what you have in a molecule. Molecule, you only have one particle. Putting a 6 in front, because students have asked me, can I just multiply it like the number in front? Absolutely not. You have to communicate like a chemist. And a chemist would say, when I have 6 of these all in one molecule, that means that I multiply the subscripts by 6. I don't put a 6 in the front. So now that says that I need C1 times 6, H2 times 6, O1 times 6, which is C6H12O6. Okay. Chemical reactions. Stoichiometry. There's the grams to moles, moles to moles, moles to grams. When I write a chemical reaction like this, makes an 2 H2 plus an O2. When I write a chemical reaction like that, for that chemical reaction, that's communicating to me that 2 moles of H2O is equivalent. Sometimes they put this little funky omega thing on top, and that just means it's chemically equivalent. But basically, it's equal. It's chemically equivalent to 2 moles, which is equal to 1 mole of O2 for that reaction. Now I can set up any ratio here and the ratio will equal 1. So when I multiply anything by a ratio of any two of these things. Any two. I could do a ratio of O2 to H2O. If I take that ratio, that is equal to 1 because all of those things are equal. If the numerator and the denominator are equal to each other, I'm just multiplying by 1. All these conversions that we do, we're just multiplying by 1. It doesn't look like 1 because we think of the number 1 only as the number 1. But if x equals 5, then 5 over x equals 1, right? These are all equal to each other. Therefore, the ratio of any of them is just 1. So we have to do grams to moles because reactions are moles. And then we do moles of A to moles of B because everything is chemically equivalent. If a question asks for grams, then we go ahead and convert the moles that we have back to grams using these molar masses from the periodic table. Is this helping to hear the whole picture? Limiting reactants. In chemical reactions, sometimes one chemical gets used up. I keep talking about the car. I will go back to that car example all year long. If we have 8 tires and 1 steering wheel, we can't make 2 cars because we run out of steering wheels and we have 4 tires left over. Now, notice I'm working with the whole numbers in that problem. Same thing with the moles. We cannot use grams for doing these calculations. We have to use the moles. And the moles react in whole number ratios. Two to 1. Actually, I should have written this reversed so that I'd have 2 reactants. So I could give an example of a limiting reactant problem. So if I have 2 hydrogens and oxygen making 2 waters, okay. If I give you information about both of these chemicals, you have to find out who's limiting. You can't just do a direct grams to moles, moles to moles, moles to grams. So that's when you use the whole chart. And the chart is our initial minus the extent of reaction to get the final. Find who's limiting. Find what the extent of reaction is from the limiting reactant. Extent of reaction is just X. And then plug X into all our equations, and that tells us how many moles of everything are left over or formed. Trying to think if I've missed anything. Can anyone think of a concept that I've missed here? I think I've done everything. Oh, physical versus chemical change. So physical changes, we had very little practice with that, but it was back at the beginning. The chemical structure stays the same. So if I have a CH4 in the beginning, I still have a CH4 at the end. So vaporizing, melting, boiling, freezing, those are all just physical changes. H2O, when you freeze water, it's still water. When you boil water, it is still water. Some people think that when you boil water, you have the reverse of this reaction occurring, and that is not true. When you boil water, you don't get oxygen and hydrogen, you get H2O. Chemical changes, you get new chemical structures. Bonds are broken, bonds are formed. And I'm pretty sure I've gone over everything. So I'm going to send you to your breakout rooms. And I'm going to wait in here. If there's a question in the breakout rooms, I mean, I'll move through the breakout rooms, but if you have a question, or actually, does anyone have any questions about the test before we? You'll come to class Thursday. You'll come to class Thursday. You will see the test in your notebook. I'm gonna send it to everyone most likely on Thursday. Like at the start of class, I will send the test to everyone. You should have a periodic table printed out. You are not allowed to use your notes. That's really important. I don't know how I'm gonna really know that you're not cheating, but I'm gonna request that you don't cheat. It's not open notes. If you want to print the test out, you can do that. If you want to just look at the test on the screen but work out the problems on your own paper, that's fine. I might ask somebody at some point in the test, I don't think I'll do this, but I might say, like, I want to see your notebook. Because if you're doing it digitally, I'll just see that you're doing it as you're working on it on your laptop. Or however, if you had the bamboo thing, I'll see that happening. And then if you're not doing it digitally, then I'm going to have a Dropbox, I think. Or I will just have you upload it into your notebook. So you'll have to take pictures and then you upload that into the notebook. And that might take 5 minutes or so. One thing I have everybody do, and I think I forgot to put this up last class, there's going to be a short 10 to 15 minute video. Maybe I'll get you in a second. There'll be a short 10 to 15 minute video that you'll need to watch tonight, or I might have already put it in the calendar as previous homework, but I don't think I did. It will not be on the test. The purpose of that is so that when we're done with the test, we're going to start the next unit when the test is over, if that makes sense. Some of you will finish the test very early, and that is not uncommon for students to finish early. If you do, I'm going to have the next unit all uploaded, and you just start the next unit. Maeve, what was your question?
I have 2 questions. First, if we finish the test, what if we're